This video is a follow-up to the video Hypothesis Testing for Proportions. In it, we'll explore some additional terminology and concepts, as well as learn how to construct a confidence interval. You need to know about Type 1 and Type 2 errors. A Type 1 error is when the null hypothesis is true, but we mistakenly reject it. A Type 2 error is when the null hypothesis is false, but we fail to reject it. The power of a test refers to a test's ability to identify a false null hypothesis, essentially to correctly reject it. The Greek letter beta refers to the probability of an error. It's also important for you to consider the relationship between confidence intervals and hypothesis tests. A 95% confidence interval, for example, corresponds to a two-sided, also known as a two-tailed hypothesis test with an alpha level of 5%. So if we have a 95% confidence interval, it corresponds to a two-sided hypothesis test at alpha of 5%. 95% in the middle and 2.5% in each tail. Let's explore some of these new concepts in greater detail with an example problem. Suppose a company is sued for employment discrimination because only 32% of its new hires are female, although 52% of all recent applicants were women. Is this evidence of discrimination in the company's hiring policies? We'll set up our null and alternate hypotheses. Our null hypothesis is HO, where P equals 52.52, and HA, our alternate hypothesis, that P is less than 0.52. So in other words, we're looking to see whether 32% is significantly lower than 52%. Is this a right, left, or two-tailed test? This is a left-tailed test. We know that it's left-tailed for a couple of reasons. One is that our alternate hypothesis states P is less than 0.52, and the other has to do with terminology in the problem. A company is sued for employment discrimination because only 32% of its new hires are female, although 52% of all recent applicants were women. This statement right here indicates to us that we're looking to see whether the number of women hired, or the percentage of women hired, was significantly less than or lower than the percentage who applied. So we are conducting a left-tailed test. Next, describe a Type 1 error within the context of this problem. In this case, a Type 1 error would be concluding that the company was discriminating against women, although they are not. If the hypothesis is tested at the 5% level of significance instead of 1%, how might this affect the power of the test? The power of the test will increase when the significance level is raised from 1% to 5%. Or rather, we should say lowered, because our threshold is being lowered from 1% to 5%. It's a less stringent test. The lawsuit is based on the hiring of 37 employees. Is the power of the test higher than, lower than, or the same as it would be if it were based on 87 hires. The power of the test is lower when the lawsuit is based on 37 employees instead of 87, because lower sample size leads to less power. Now, let's take a look at an example of constructing a confidence interval for a proportion. A study of 312 10th graders found that 48% experienced difficulty sleeping during the week prior to taking standardized achievement tests. Create a 90% confidence interval for this proportion. To create our confidence interval, we need to begin by identifying our sample size, which in this case is 312. Sample size is represented as n, so I'll write n equals 312. I need to also identify p hat, which is our sample proportion. In this case, p hat is equal to 48%, which I'll write in decimal form as 0.48. Using sample size n and p hat, or sample proportion, I'm going to calculate the standard error for p hat. I'll then be using this value along with my critical value for my confidence interval to construct a margin of error. And that will help me to create a confidence interval. Here's how we'll do it. The formula for the standard error of p hat is standard error of p hat equals the square root of p hat times q hat divided by n. Now we know that p hat is 0.48. Q hat is the complement to p hat. So if the sum of all probabilities in a given sample space is equal to 1, and we know that p hat is equal to 0.48, q hat must be equal to 1 minus 0.48, which equals 0.52. We divide the product of p hat and q hat by our sample size, 312, and this gives us an approximate value of 0.028. That's my standard error for p hat. Now I need to determine my critical value for a 90% level of confidence. It's best to memorize the critical values at 90, 95, and 99%, as those come up frequently when you're taking a statistics course. And in our case, the critical value for a 90% confidence interval is 1.645. Our critical value at 90% is 1.645. If you're not sure about this value, you can use your inverse normal function on your graphing calculator, or you can use a z-score chart, because our critical value is a specific value of z. It's the value of z that represents the cutoff at a 90% level of confidence. In other words, at a 90% level of confidence, our cutoff value for the upper end is 1.645. Our cutoff value at the lower end is negative 1.645. So the boundaries for my 90% confidence interval occur at plus or minus 1.645 standard deviations away from the mean. Using our standard error for p hat and our critical value of z, we'll construct our margin of error. So the margin of error equals 1.645 0.045 times 0.028 and that results in a margin of error of 0.046. Therefore, our confidence interval is p hat 0.48 plus or minus 0.046. We can also write those as percentages by moving our decimal 2 to the right. So you could represent it as 48% plus or minus 4.6%. Another way to represent a confidence interval is to simply write the endpoints in a set of parentheses. So we could say 43.4, comma, 52.6. These values are obtained by adding 4.6 to 48% and subtracting 4.6 from 48%. So if we look at this within the context of a normal model, here's our 90% confidence interval. We have our lower bound of 43.4 and our upper bound of 52.6. P hat is 0.48, and that's found at the center of our model. In conclusion, we can state we are 90% confident that the true proportion of 10th graders who have difficulty sleeping the week prior to taking standardized achievement tests is between 43.4 and 52.6%.